So we talked about the differential cross-section, d sigma, and we said that we had to work a little bit to produce a d-ellipse for the m-particle final state. But after having done that, there was just a simple factor that we had to put here to compensate for Lorentz transformations. And the physical object, the object that has all the physical information, was some matrix element that depends on the incoming particles and the outgoing particles. This was a matrix element obtained from the overlap of the state PA-PV, or the matrix element of the operator T, except that we pull out a momentum-conserving delta function, because clearly this object has to vanish whenever momentum is not conserved. So it's not a function, it's a distribution that only has support on momentum-conserving data. So all those words in equations are just telling us this, okay? Well, this was coming from an operator we call the scattering operator, or the S-matrix operator, as people call it. And this was our definition for T. And motivated by Tibra's question, I ask you to find out what the unitarity of S implies for T. Okay? And S had to be a unitary operator because it's an operator that all it does is to relate two different descriptions of nature. Okay? So it had to be unitary. So I also said yesterday that during these lectures, our goal is to see how far we can go by only assuming unitarity, or by only using unitarity, plus another ingredient. That's what I didn't say yesterday. So we're going to try to see how far we can get using unitarity and Poincaré invariance of these matrix elements. Okay. Let's start with unitarity, because it's basically what we just following Tibra's suggestion. Okay. So I had a different plan, but Tibra's idea was so good that I decided to change everything. So I'm sure you all worked this out, right? So if we just put it in here, we get the identity plus IT is equal to the identity minus I. Oh, sorry. I want to put the dagger here. So I'm going to compute the dagger here. And then the usual one here. This is equal to the identity. And therefore, this means on this side, I have the identity. This with this is this. And then I have IT. And then I have, this is, what is this? This is minus with plus. T is equal to the identity. And therefore, the dagger T has to be equal to I T dagger minus T. Okay? Modulo, sign mistakes, and factors of 2 and errors. Now, but you all checked this yesterday, right? So this is correct. All right. So what do we do with this funny-looking equation? It's indeed a funny-looking equation. Well, we do what we are always trained to do whenever you see an operator somewhere. You sandwich between some states and see what the matrix elements of this operator is. After all, this is an operator, and this is also an operator. So what are the matrix elements that would be nice to use? Well, we would like to use, of course, PA, PB, that state. And I'm going to call this, it's going to take me too long to write PA, PB all the time, so I had to give a name to this. I'm going to call it I. They're incoming particles. And P1, P2 up to Pn, I'm also going to give a name. This is bad. What does it look like? Looks like the vacuum, right? So I couldn't call it O. Let's call it F for final states, okay? So these are initial states, these are final states. Any other suggestions? I'm open to suggestions about notation, okay? Very good. All right. So let's sandwich this with these states. So let's put them. So let's try. So that equation implies the following equation. Okay. Now, it's often convenient whenever you see the product of two operators to introduce what people sometimes call the resolution of the identity. In other words, or the fact that the basis that we chose of states of our Hilbert space is complete. That statement is given by saying that the identity in the whole Hilbert space can be written as this operator plus many other operators. This, yesterday we took to represent the vacuum, right? So now we have the vacuum or the projection operator onto the vacuum. Now we have to add what? What would be the next step? The one particle. Yeah, so we have to sum. In quantum mechanics, we are very familiar with summing over all the states, but here they are continuous, okay? So we have to integrate over them. In other words, we're going to put here the one particle states, P, but we have a continuum of them. Not only we have a continuum of them, so we have to integrate over them. But we know that not all of them are physical, okay? So we have to put, of course, that's a problem of writing something and then going back. Okay? And not even this, we know that we have to put something that people usually denote as a plus, and that's just a shorthand notation. So the plus means putting this thing there that we had yesterday. Okay? So you're also supposed to, the plus reminds you to put it in. Okay? Now we go to the two particle states. And I use my nice notation for that. And so on. Okay? So let's start with this guy. So we're going to put the identity inside here, of course. That's the only natural place to put it. And we're going to expand this. So how about the first term? The first term gives us I, T dagger, the vacuum, T, F. What is this? What do you think? Remember that these matrix elements are constrained to satisfy momentum conservation, right? So that means that this object, also this object, but let's look at this object, is something times a momentum-conserving delta function that tells us that the momentum of this guy has to add up to the momentum of this guy. So the momentum of the vacuum is 0, and we have the sum of the momenta of the final states. But for us, that sum is generically not zero, right? Because we have some incoming particles, which we're assuming their momenta doesn't add up to zero, okay? That would be a very strange situation, right? That you're scattering particles and exactly their sum of momenta is identically zero as a 4-vector, okay? So we're going to say that this is zero because this is not satisfied for the states we're considering at the moment, okay? Yes?
One thing, when you put the ellipse 2 out there, the last class we had inside the ellipse the conservation of momentum of the ingoing and the outgoing, right?
Thank you. So the hat means without momentum conservation. Yes. Very good. Very good. Yes. This is. You didn't say how much. But then how am I supposed to write when this is there is a little problem with the. Okay.
Yeah, they were supposed to change it yesterday to that side, but they didn't. I'll remind you.
Well, we will have the same problem, I guess.
Well, it can be
maybe
to the very corner.
Okay. Well, we can spend a whole quantum field theory course, basically. Not the way it's taught in any place, but we could design a whole quantum field theory course in order to study the consequences of each of these terms in that equation, okay? But since we don't have all that time, we're going to study the consequence of this term, okay? So this is for this course. This might be for the next course. And the others, well, good luck with that. Yeah. Okay. Okay, the top one is now fine, so we can change boards. Very good. So let's use the first term, okay? So what does the first term tell us? Well, it tells us the following. We have integral d4p delta plus p squared minus m squared of this, and we have t final. Okay. As I said, plus other terms has to be equal to. Here, let me do something. I don't like the dagger operator there. So I'm just going to change it for this. And I'm going to put here what we have. Okay. Very good. Now, each of these guys, again, is something. Well, I also would like to change this by P, T, I star. Okay. Now, this guy has momentum conserving delta function that tells us that the sum over the incoming particles. Actually, let me introduce a notation for the incoming particles. Well, we know what they are. They are PA plus PB. Okay? They are the incoming particles. Minus P has to be 0. Okay? This one also has a momentum conserving delta function of the form sum over Pi from 1 to n. Remember, these are our outgoing particles. Minus P has to be 0. if I combine these two delta functions, what do I get? Say, if I use on the support of this one, what does this one become? Very good. So on the support of that, this becomes the sum over I from 1 to n, pi minus pa plus pb. Okay? Very good. So I should remember that this is only true on the support of this one because this one is multiplying here. Now, the same thing happens here. In other words, this thing also has an overall momentum conserving delta function of this form. So I'm going to write it explicitly, but I'm going to do it like this. So I'm going to put the m from f to I star, so I can actually remove the I, minus I m from f to I times a momentum conserving delta function. Okay? Very good. So as distributions, if I remember that everything has to be done on the support of these delta functions, I conclude that this has to be equal to whatever I have on this side. Okay? So what do I have on this side? Well, I have a delta function that actually performs, that can allow me to perform the integration over P. Is that clear?
Question.
Yes.
How do we know that M is symmetric? Shouldn't it be M from I to F? Or, I mean, what should?
Yes. Thank you. Okay. So if I use this, to carry out the P integral, we find something that looks like this. Times the matrix elements here. So we find M from I to P star times M from F to P. Okay? This has to be equal to I. Of course, this plus the next courses, okay? So I have to confess something right now. You will never see this equation written anywhere, at least not in modern books. And the reason is the following. Is this generically non-zero or not? You see, this term here is only non-zero when this argument is zero. Is that generically true? Is it generically true that when we scatter two particles, their momenta add up to something whose square happens to be exactly the mass square of a particle? That's right. In general, it's not true. So this is generically not true, and that's why in the books, they don't even bother to write this term. Okay? But I'm going to assume that we're very, very close to a region where that happens, and I'm going to exploit that. Okay? The reason I want to do that is that I want to understand what this function is. And in order to understand what a function is, okay, especially if the function is assumed to be analytic, all you have to understand is their singularity structure, right? If I tell you that I have something that is a rational function of some complex variable, and I tell you that I know all its poles and all its residues, can I construct the function from just that data? That's right. If I tell you that I have a function that it has branch cuts, but I know exactly the branch points and I know the discontinuities, and I know all its poles and residues, can I construct it? The answer is yes. Okay. So, yes.
One thing, so we take just the one particle term, right?
Yes.
And we, I mean, at the right-hand side, we have something that is similar to the left-hand side, but the higher order terms, I mean, the 2-particle, 3-particle,
yes,
those add to 0?
No, they are here. Yeah, you don't see it because it's along your line of.
Oh, okay.
Yeah, sorry. So I encourage you to work out the next term, the 2-particle state. That one is always there, no matter what happens, okay? Because it doesn't impose any special condition on the kinematics of the external particles. So work out the 2-particle state and see what it looks like, okay? The contribution from the 2-particle states. So I'm going to work in something that I like to call the rational function approximation. So once again, you will not find this terminology anywhere, so I just made it up, okay? So I'm going to assume that this function is a rational function, okay? That assumption will break down once I take more terms from here. But since I'm not considering those terms, I'm going to be fine, okay? So this is a rational function of the external momenta. If I find what all its singularities are, I'm going to be in great shape, okay? That's why I want to keep this term. Now, this term is telling me that if I go to a region of momenta that is very, very close to the place where this delta function is satisfied, this will have to do something very special for this equation to be satisfied, okay? That's what I want to find out. So let's do it here, okay? Close to PA plus PB squared equals to M squared. So I'm working in this regime. Let me write the delta function of PA plus PB squared minus M squared. Well, let me do it here first. So this distribution is something that we can write as a limit Okay, have you seen this before? Okay, if you haven't seen it, then prove it by doing the following integral. Okay, so if you don't believe that is true or you haven't seen it, you should not assume that this is a delta function yet. I mean, you just take it there. You put a test function here that is assumed to vanish at infinity, even in the complex planes. Eh? And then plug that in here and translate the integral into an integral over a complex plane, over a complex variable, with a contour equals to the real axis. This is our contour now. Deform the contour and show that you get phi of 0 at epsilon equals to 0 when you take the limit. Okay? Now I'm going to use that identity for this delta function. So it's going to be, I'm not going to write the epsilon, the limit all the time. So I'm just going to assume that I'm working in the limit. So you get PA plus PB squared minus M squared minus I epsilon minus 1 over PA plus PB squared minus. Okay? So once I do that, I see that this term also splits into two. Okay? And if these guys are rational functions, and they are going to develop a singularity when this happens, it must be that each one of these guys goes into one and one goes into the other. That's the only way this as a rational function and this one as a rational function too can have a chance of producing this delta function. Okay? So I'm going to assume that precisely they go in the same way. This one could be to the right, could go to the m on the right, meaning this one, and the other one to this one, or vice versa. But I'm just going to assume that the one that I wrote on the right goes to this one, and the one that I wrote to the left goes to this one. Okay? So once again, in our limit of PA plus PB squared going to m equals 0, to m squared, we should find that our matrix element has a singularity of the form PA plus PB squared minus m squared plus I epsilon. In fact, if we work out even the i's, that will give us an I, and we get this on top, which I'm going to write here as this, and then I to P. Okay? Very good. So isn't this nice? Unitarity is telling us that if I assume that this is a rational function, it's telling us that it has poles. Okay? It has poles whenever this can happen. Not only is telling us what the poles are, it's also telling us its residue. And its residue corresponds to the product of these two things. Now, people don't usually write these m's all the time. They draw pictures, which is much nicer, of course. It takes less time. So I'm going to start drawing pictures because I'm getting tired of writing all these m's. Let me introduce a picture to represent this, where I have our PA and PB as incoming particles. So this represents the scattering. They are coming, doing their things, and then coming out as outgoing particles. So we are finding that in the limit, this thing behaves as, did I get all the signs right? Is everybody checking everything? Yeah, the reason I'm complaining is that the picture doesn't look like this picture nicely. But, okay. Sorry?
You switch your from I to P or F to P, reverse the order. It's the same thing Jason was saying.
Right. So really what I wanted to get, I mean, what I should have gotten, is something that looks like our PA and PB going into P. We have times this weird object, well, the other one should have been the other one that was weird, not this one.
The second line, you're computing m of f to I rather than I to f.
Actually, this one was then something like this. This guy.
No, that's okay because there.
Oh, this one is okay, I think. Something like that. Okay, so that's an exercise for you to work out exactly what these guys were supposed to be. It's a simple, you just have to be careful not to mess up with the stars when you complex conjugate and reverse, and be consistent with your notation of which guys on the left represent, which guys represent incoming particles and which guys represent outgoing particles, okay? But at this point, we're not going to worry about what this is. All what I want you to take from this is that unitarity is telling us already that the function has poles, and its residues, if you do it correctly, can be computed just from unitarity, okay? Very good. Now, there is something else that I want to mention. which is actually an experimental fact. And the experimental fact is that if we compute the matrix element, or we measure the matrix element of any interaction where you take some particles, let me say that you have some particles in the initial state, and they go to some particles in the outgoing state, okay? This, as a function, allows you, this is actually surprising, it allows you to compute this other function, where you remove this particle from here, and you move it to the other side, and you put a minus sign in it, okay? So what do I mean by this? Well, what I mean by this is that, and actually I'm going to assume right now that this also holds for the m's and not just for the mod squares, okay? So I'm going to say that if you have if you know this as a function of momentum, okay? In our case, it's a rational function, imagine. We have a rational function that depends on this momentum. Just checking, when I say rational function, what comes to your minds? What? Yeah, but well, it's a function that is the ratio of two polynomials in the variables, okay? That's what I mean by rational function. Yes?
Okay. I'm lost. I don't understand why there's M of F to P and I to P. I don't follow that part.
F to P, where? Oh, the top one.
Yeah.
No, I'm just reading what this is. Right? I expanded this delta function using my little trick over there.
All right. Okay.
I'm just translating that equation here. Okay. Okay. So the claim is that if you compute this, okay, and you take it as a function, this thing agrees with this matrix element. Now, of course, if you are in the region where this PB is actually an incoming particle with positive energy, this formula evaluated on that PB doesn't make any sense. It's not physical. But as rational functions, they are the same object. So you can now, after having computed this one, you can just simply forget how you got it. Somebody gave you this function, and now evaluate it on a PB that makes this physical as an outgoing state. So it's completely remarkable. Well, at the moment, it doesn't look remarkable. You should all be surprised, saying, wow, this is unbelievable. But maybe it's because we haven't put it together with the previous statement. You're going to see what's going to happen if we do. So this is called crossing symmetry. Okay? Now, yes?
So is this kind of, when you say an experimental fact, could we say like that one could be a Compton scattering, and the other one could be annihilation?
Yes, but we haven't discussed any of those. Yes. Just saying that it's a fact, and it's very surprising. Now, let's try to put it to the use and say, let's go back to our original experiment. We had PA, PB going to just two particles, P1 and P2, okay? From unitarity, we know that this rational function should have a pole of the form PA plus PB squared minus M squared. In fact, it should have one like this for every possible mass that is in your theory. Even more surprising. Okay, but here let's assume that there is only one kind of particles, and that all particles have the same mass. So there is only a single pole like this. Now, according to this should be the same rational function as the one that I get by, say, putting P2 here with a minus sign, and then putting PB there with a minus sign. But unitarity for this one tells us that the function should have a pole, but where now? It should have a pole at PA minus P2 squared minus M squared. How about that? The same function should have these two poles. It's the same function. It's the same it's the same rational function. So somehow this guy, when we compute it, should have this pole, but it should also have this pole. Okay? What else can I conclude by playing my little game of crossing? Yeah, it should have another one, even another one. So what's the other one? 1 over PA minus P1 squared minus M squared. So let me just a second. Let me draw what this looks like. So we have A and B, 1 and 2 coming out, or we also have here A and 2, 1 and B, or we also have A and 1 and 2 and B. Okay? Yes?
So originally we started saying this is an experimental fact, and then you tried to argue. I missed the explanation of why this being a rational function justifies this being true. Was that an argument, or are we just saying for now it's an experimental fact? We don't know why.
Remember, our rational function is an approximation, so it's not even true.
Yeah.
Okay.
So,
the experimental fact is that this is true.
okay, fine.
The assumption is that this is true, and I'm just using it.
Okay, fine. And
Yes.
okay, fine. And this doesn't follow from some delta function that was originally there or anything.
No? How about that?
Okay.
Yes.
You made the choice of leaving PA fixed here, right? But I can also have the poles at PB minus P1 and...
Well, momentum conservation tells us that this is nothing but PB minus P2. That's momentum conservation, right?
Okay, right.
In fact, these are the only 3 possibilities that you can have.
Okay, so that,
Yes.
that expression you have there for M, it's implying you have momentum conservation as well.
Yes, yes. Remember, everything I remove,
You remove the deltas, but you are...
I warned you to keep that in mind, right? I removed this. But at the price of always remembering that everything I'm saying is on the support of momentum conservation. So there are 3 things here. These are the only things that can appear in our function. And in fact, when you have 2-to-2 scattering, people like to give names to these things so that you don't have to write P plus P and all the time. So people call this one S. This one, well, it depends on your taste, T, and this one U. And those are called Mandelstam variables. Okay? They are not all independent, so assume that all P squares give you the same M, okay? And compute S plus T plus U. Okay, that's an exercise for you. Okay, in any case, what I want to get is the fact that just from unitarity and crossing symmetry, I can conclude that my matrix elements in my rational function approximation, we know exactly all the poles they have, and not only that, we also know the residues. Okay? Very good. There is one catch, of course, which is that we know the residues, but in terms of a smaller amplitudes, of a smaller matrix elements, right? So look at what happened there, right? So we know this one in terms of this one and this one. But if nobody gives us the original ones, the smallest ones, then we're going to be in trouble, right? We cannot compute things. So somehow, this hints that there must be some recursion relation somehow lurking behind the whole thing and telling us how to construct bigger matrix elements from smaller ones, okay? So that would be the hope, yes?
Can you just go over the big picture again, how we got from only the assumption of unitary and only one experimental fact to these three things?
Well, and a few more assumptions, and then a few, yes?
Yeah.
Okay. Well, so we started with the assumption of unitarity. We applied that to our matrix elements there. Let me put this higher. Oh. Okay. So we started with the consequence of unitarity. We decided to, if you see the top one over there, unitarity implies many things, okay? It implies constraints between the left-hand side and the right-hand side for every sector in the resolution of the identity. So my first assumption was that I can do something sensible by only looking at the first, or if I forget about the vacuum term, if I look at only the one particle states, okay? So that was the first assumption. From the top board, right? I'm only keeping the one particle states. I'm putting everything else as dots, okay? First assumption. Well, we had unitarity. Now we're assuming we can do something sensible with just the first term. We work all this through. We concluded that most books will tell you that they won't even bother to write the first term because it generically vanishes, okay? So in all books, they will start with the second term, or the two particle states. Okay. We decided to not do that and explore this term and see how much use we can extract from it. We wrote our delta function in that form, in the sum of two terms, because on the right-hand side, we also have the sum of two terms. And I'm making the assumption that this, as a function of external momenta, can be approximated as a rational function. Maybe it's not true, maybe it's useless, who knows, okay? But I'm assuming things. I just want to see how far I can get, okay? So I assure you it's not going to be a waste of time. Otherwise, I wouldn't be doing it. But these are the kind of things that you just, when you're in your office, you make assumptions. You start working out things. You get to some point, and then you go back and say, well, did I get something useful or not? Yes?
What justifies your assumption here that these are rational functions? I mean, you're looking for poles.
Well, the justification is that if I try anything else, it's going to be more complicated. So my approach is always to try the simplest thing first, and then make my life complicated as I go, okay? Not make it complicated from the beginning, and then reduce to the simple cases. But different people have different approaches, yes?
Maybe it's a stupid thing, but where do you get first the term of f going to p and then the other one?
Yeah, I told you I messed it up somewhere, but that's your job somewhere to fix that. Okay. I hope it's clear that it's just. I mean, we could do it, but time is. So Tibra will do it. Okay, very good. So we're concluding that the same object, this guy, should have these three poles. A rational function with these three poles in it. Okay?
So you've got 4 places you can switch around between. You got 3 steps.
No. Real. Okay.
Sorry, and could you tell, like, physically what this experimental fact means? Because I cannot.
Well, that you measure your differential cross sections. You model your function. You have it there. some cosine of the angle with P and so on, or something that depends on P dot P of the external momenta. I mean, something that depends, say, for 2 to 2 scattering depends on ST and U. It's some function that depends on ST and U. Then you go ahead and perform the other experiment, and you do it, and you get a rational function. Then when you see the two rational functions, you say, oh, they are the same. How come? I mean, that's life. Well, now you say, well, let me try to use it. Okay. All right. So now we're going to shift gears completely because we have to get some information about the building blocks. Okay. And the building blocks are these very small matrix elements. Okay. When we have two particles going to one, or even 2 to 2 sometimes, we'll have to work them out. But those, in order to construct more general matrix elements, using this procedure that I told you, we will have to somehow understand these basic ones. Okay? And the claim I'm going to make is that just by imposing Poincaré invariance of the mod square, we're going to get very, very far along that way. Okay? So let's try that. Okay. And in order to do that, we have to go back and study the basic building blocks which are one particle states. Okay?
Freddy, just one notational point. When you said we can take PB2 minus PB on the other side.
Sorry, when I say what?
The experimental fact.
Yes.
You're also like replacing it with something else. Like it's PB is switching place with another momentum, right? The other momentum that is going to is coming to.
No, not necessarily. I'm not switching anybody. The dots are the same. Oh, very good. So in this, in what I did below, I did the operation twice. Okay? Thank you. Yes. So I had to do the operation twice to get the 4 particle statements that I wrote there. I did it without thinking. Okay. So we want to study what happens to one particle states under Poincaré. Okay? So just to set up our notation, we know that on coordinates, Poincaré acts as follows, where this is a Lorentz transformation, this is a translation, and together, when people find a group that has this structure, they usually denote it, or they usually call it, the inhomogeneous version of the one that you have here. So this would be inhomogeneous Lorentz group. But this is too long, so I'm going to call it Poincaré. Okay? But you will also see this in many places. Just wanted to mention. All right. So, once again, we have to invoke our friend, Wigner. And I would like to encourage you to go through Appendix A of Chapter 2 of Weinberg, where he discusses the proof of the theorem. Okay? Once you go, read it, deeply digest it, come out with even a simpler version, you come and tell me. Okay? Okay. So, if we have any quantum mechanical system again, and we have 2 descriptions, one by an observer and another one by another observer, and the two are related by a Poincare transformation, then it must be that there exists a unitary operator such that we can go from one description to the other by using our unitary operator. Okay? Good. Now we are going to say that, well, such unitary operator must exist for every transformation, for every Poincare transformation. So a Poincare transformation is a collection of pairs of objects, Lorentz transformations and translations. Okay? So this is a Poincare transformation. And we're going to assume that there exists one unitary operator per Lorentz transformation. Yes?
One thing, yesterday in the tutorial we saw that, for example, the Poincare group, which is a SL2C, is not unitary, right?
What do you mean it's not unitary?
I mean, any element of SL2C doesn't need to be unitary. I mean, what you're implying with here by Wigner's theorem is that you can find unitary representations of the Poincare group.
Yes, that's right.
U is an infinite dimensional representation of the Poincare group.
Well, these guys will be infinite dimensionals because they will act on this monstrous Hilbert space, right? Okay. So, indeed, I was just going to mention that this map cannot be just a general map. It has to be something that is called a representation of the group. So we are representing this abstract group as a set of operators acting on some Hilbert space. So if this is a representation, it means that if we have the composition or the product of two operators acting on the Hilbert space, on any element of the Hilbert space, it must be the same as another one where the entries are exactly what happens with the composition rule of the group. Okay? So what's the composition rule for the Poincare group? Well, you can deduce it from here, right? Imagine you perform one transformation and then another one, and read out what the composition rule is. So you compose the two Lorentz transformations, then you apply the first one to the second one, and you add this guy. So that would be the translation. Okay? In particular, this means that there must exist an operator called the inverse of any transformation, such that when you do this, you get an operator which does nothing, which is represented by the identity operator, acting on your Hilbert space. Now, from this composition rule, I can tell what this thing is. It has to be exactly the operator evaluated on the inverse, which must be something like this. And then I have a translation, which we have to be something of this form. So this we said is, so we started at 10:30, and we can go 20. Okay. All right. Very good. Okay, so we have this. Now we want to do something that is something that Anna explained in general for Lie groups, which is to study its algebra. Okay? So whenever you have a continuous group, you can always try and look at what the group looks like very near to the identity. Okay? So if we do that here, well, we can spend the rest of the lecture just doing that. But I'm going to assume that I'm going to say that I'm not going to be interested in what happens when I move slightly away in this entry, but just what happens when I move slightly away in a translation. Okay? So I'm going to perform an infinitesimal translation. No Lorentz transformation whatsoever. Okay? So that will be your exercise. You can try to go through the whole thing and consider what happens when you do that. Now, when we do this, since the group is continuous, this must be very close to the identity, because epsilon is infinitesimal. So by convention, well, the next correction, or the correction to this, must be something that is proportional to this translation vector that is infinitesimal, and whatever multiplies this, I'm going to denote as P. Okay? The minus I is just convention. So this is convention. The I is there so that unitarity means that this P has some nice property, right? It's Hermitian. Well, it's the same computation as the one we did for T, except that in the T dagger T term, we drop it because we get an epsilon squared. Okay? And epsilon is infinitesimal. So we can just drop it and conclude that P dagger has to be equal to P. Okay? Very good. Now, we're not going to do it here, but by studying the full set of elements, okay, in the Poincaré group, we can conclude that this has interpretation of the momentum operator. Another way to see it is that if you exponentiate this action to produce a finite transformation or a finite translation, you will find that this simply exponentiates to this operator acting on your states. And from quantum mechanics, at least the spatial components, we know that they look like the components of the momentum operator. And if you look at the P0 component, this would actually correspond to the Hamiltonian, which would correspond to translation in time. Okay? But for our discussions, we will just declare that this is a momentum operator. Okay? Now, what do we want to do? We want to see how this guy itself transforms under a Lorentz transformation. Okay? And I'm going to call that little exercise we're going to call it fun with operators. Maybe. That is, if I get it right, it will be fun. If I don't, then it's just going to be a mess. Okay, so what do we want to do? We want to take, this is what we want to compute. We want to take a Lorentz transformation. Let me check exactly where, okay. So under a Lorentz transformation, under a general Poincaré transformation, I want to see what happens to our infinitesimal translation. Okay? So is everybody familiar with the fact that an operator transforms like this when you perform a transformation? Okay. Very good. If not, then you can ask Anna and Tibra why that is so. But I'm not going to use it. I'm just going to work this out as an identity. Okay? So if you don't know what I just said, don't worry. I just want to compute this and see what happens. Okay? Well, the first observation is that I can replace the dagger by an inverse, right? Because this is unitary. Everybody's happy with that? Now, that's why I went through the exercise of computing what the inverse was, because now I can replace this by what it is. Okay, so this is what I want to compute. I shouldn't be doing this, really. I mean, it's too lazy. This, and this thing is u of lambda inverse minus lambda inverse A. Okay? Now I want to compose all this. Okay? Just want to write this as a single operator. You might say, well, good luck with that. And you might be right. So let's first compose these two guys. So what do we get? We get this guy with this guy. Nothing interesting. Now this guy acts on this, and then we add A. Okay? Very good. Now we have to compose this with this guy to get our final answer. Okay, now it's the turn of this guy and this guy to go together and give us something. So when we compose, we get this guy composed with this guy, give us the identity back. Okay? Now this guy is supposed to act on this guy, and we're supposed to add this to that. Okay? Now this is the identity matrix, and this drops out with this, and we get u I lambda epsilon. That's pretty good. Now we found our identity, and so far we're having fun because it seems correct. Okay. So we found our identity, which says that this operator acting on this operator, assuming this is infinitesimal now, I mean, this was just true in general, but assuming that this is infinitesimal, I can write it now as and again, this is infinitesimal, so I can also write this as the identity minus I lambda epsilon mu p mu. Okay? Now, clearly, the identities cancel on both sides because this operator with this operator sandwich acting on the identity will give me back the identity, and that cancels with this term. Then I conclude that epsilon mu let me write it like this better. I conclude that epsilon mu contracted with the action of these guys on my momentum operator must be equal to okay. So this is almost what I want, because what I really want is to see how this guy transforms, not this combination. But this epsilon is infinitesimal and generic. So this must be true component by component, and that's what I would like to do now. I want to extract one component of that. Sorry, let's do it on this. Okay, how do we extract a component? Well, we have to somehow write this in a form that looks like this, exactly like this, so that we can read a given component of mu and a given component of mu there. And that's what I'm going to try to do. Let me change this index. It's a dummy index, so I can just write it as rho, right? No problem. Now, what do I mean by this? Well, I mean exactly what I have there. It's the action of this guy. So I'm going to put in general, some crazy indices, alpha, rho, epsilon alpha, p rho, okay? So I still have to massage this because I want to extract something that has the index mu here in order to make it look like that. Okay. So what do I have to do? Remember, the index mu is whatever index contracts with rho. Okay. With p, sorry. So maybe I can change this index. Sorry. Really the alpha. Yeah, we can change that by a mu. But this doesn't look quite right.
You can pull out the.
I mean, if you the rows, if you make them mu's, then and you replace them.
So it seems to be saying that
We just want that.
this seems to be saying that this thing is this, right? But somehow it doesn't agree with what I have in my notes. Oh, you know what? I see. Oh, of course. The reason is that I had this index down, right? And if I want to have the Lorentz transformation on something that has the index down, I have to use the inverse Lorentz transformation, right? So not this transformation, but this transformation. Okay? So how is this related to that transformation over there? Well, this thing is eta rho alpha, eta mu beta of lambda alpha beta. Okay? So this is the one that we had written over there. But this is the one that I want because it's acting on this index down. Okay? So indeed, it was wrong, but now it's right. Okay? This is the transformation that I wanted to get. Okay. Almost fun. Very good. So now that we have control on what this operator is and how it transforms under Lorentz and the Poincare transformations, we're going to finally be able to define what we mean by our one-particle states. Which we have written down all this time, but never defined. So our definition is the following. We look in our Hilbert space, and we look for all eigenvectors of the momentum operator. Okay? In general, now we can be pedantic as you wanted to be yesterday. So in general, these things actually carry more indices. Okay? So following Weinberg, I'm going to use the notation sigma to mean any other index. Any other property. That these states in our Hilbert space can possess. Okay? So they are defined to be eigenvectors of the momentum operator. And the eigenvalue is precisely what we call the momentum of that particle. Okay? Now we want to study how these states transform under Lorentz transformation. Only under Lorentz, okay? For the time being, we will only consider Lorentz. So I'm going to set to 0 the translation. So this is the 0 vector. In order to save time, because we don't have much, I'm going to denote this as U of lambda, remembering that there are no translations, just the Lorentz group. Okay? And I want to ask, what happens when I apply a Lorentz transformation to our vectors? What do I get? Sorry? Yeah, so it's reasonable to expect that we're going to get something where P is going to be transformed, right? But let's actually prove it. So not many chances of proving things on the blackboard, so let's actually use it. Let's apply the momentum operator to our state. Okay. But if we look at this formula here, this formula implies is that if we consider U of lambda inverse, say 0, we don't have to consider, this is true for any A, so we can set it to 0, P mu. And then I put here, I'm now using this in terms of lambda inverse. So this is lambda A of 0 is equal to lambda inverse rho mu P rho. Okay? I'm just using this formula for a lambda, which happens to be lambda inverse of the transformation that I'm doing there. Okay? Is that clear? So I'm replacing here lambda by lambda inverse. And when I do, I can cancel this inverse, right? So I just get U. And this thing is what we have acting on the operator. So we conclude that this, acting on any operator on our Hilbert space, must be the same as this thing. But this thing is nothing but the original lambda with the indices flipped. And we have the U acting here. P rho. Okay. And what is this transformation? Well, that gives us mu rho U of lambda P rho. So now we can use this operator instead of this one and act on this state. But when we act with a momentum operator on this guy, we get its eigenvalue. So let me write it as mu rho U of lambda P rho P sigma. This thing, by our definition of one particle states, is little p rho P sigma. And this gives us this with P rho U lambda of P sigma. That means that this state must live in the subspace of the Hilbert space of particles with momentum lambda p. So this implies that U lambda P sigma lives in the space spanned by all vectors of all one particle states that have momentum lambda p, because that's their eigenvalue. Okay? And if this is true, well, it means that we can expand it and write it explicitly as a linear combination of all those. So U lambda of P sigma is equal to the sum over all possible values of these properties of the particles, over all possible particles, with some coefficients that depend on the Lorentz transformation we made times this. Okay. Now, our job is to classify all possible ways this can actually happen. It sounds very complicated. And in fact, it is complicated if we just try like this. But there is a trick that will make our life simpler. Okay? But I'm not sure we have time today to actually go through the trick. But this is our goal, is to classify all possible ways to get, or all possible coefficients that we can write here. This, in terms of Lie groups and Lie algebras, is called classifying all possible representations. Is to classify all possible representations of the group. Okay. The reason we're classifying which are the representations here really are the vectors with some given momentum and some set of properties. Yes.
So I missed something.
Yes.
That thing in the bracket, the second bracket, that's a set. What is that set again? That
So I can write it. It's a set of all states that have eigenvalue lambda p, which means that we can take all possible values of sigma prime. I haven't told you what sigma prime is. I'm just saying, well, if there are tons of them, we have to consider all of them. Okay. So what we're going to do tomorrow is to try and classify what these guys are. Okay. And that classification will classify all the possible particles we can expect to see in nature. Yes?
If sigma prime, like if we had no extra index, like what would we get? That equation would just be trivial, right?
Yeah, if we didn't have any sigma, in fact, it's clear that that's one possible representation, right? One possibility out of the whole set of possibilities would be to say that there are regions in our Hilbert space, sectors in our Hilbert space, where particles are only labeled by their momentum. And therefore, when you transform them, they only transform to this guy without anything else. And those particles have a name. What's their name? Anybody knows? Something that is a scalar particle. That's right.
One question. You decided to begin with the translations, right? And taking the generator of translations and then performing Lorentz transformations and see how these generators transform, right?
Yes.
Why are you allowed to do that? Like taking both translations and Lorentz transformations independently? I can begin with just taking an element of the Poincare group, right, and expand it near the identity, and somehow obtain the generators of the Poincare group, right? And I will come to the same results you have here.
I didn't quite understand the question. Okay. So you're saying why? I'm free to act on my Hilbert space with any operators that I want and see what happens, right? Every Lorentz, every Poincare transformation goes into one operator, one unitary operator, right? From infinitesimal translations, I found another operator, which is called the momentum operator. So in fact, a vector of operators So we have, well, we haven't proven that that set of operators, P mu, transform as a vector under Lorentz. Well, we have. We already discovered, so I can properly say there is a vector of operators. And then I can apply them to the Hilbert space.
Right, I understand that. I mean, you take an infinitesimal translation and you get the generated translation. But what about taking a general Poincare, general element of the Poincare group and perform an infinitesimal Poincare transformation?
Yeah, that was your exercise.
Okay.
Yeah, you all heard that, right? When we were discussing that, I said, well, I'm going to do everything here. I'm going to only consider infinitesimal translations, but I wanted you to consider the more general case where you also consider infinitesimal Lorentz transformations.
Okay. And the other thing is that here you define the eigenvectors of the momentum operator, right?
Yes.
So it's kind of convenient to define it this way, because if I take an infinitesimal Lorentz transformation, then I can define other vectors that.
Yeah, this is in fact like for convenience, and in fact it matches what we have been doing from the beginning, our intuition that we want to describe particles by their momenta.
Okay, but intuition also says that, for example, the mass for different particles should be.
Oh well, but that's precisely that.
It's inside. Okay.
Yeah, it's inside here. That's a property that is Lorentz invariant, right? Yes.
Scalars can be charged, so sigma is not a charge, it's not electric charge.
No. The Lorentz. Remember, here we're asking what happens under Lorentz transformations, right? So, that's a very good that's a very good thing. People usually talk about, this particle or this object is a vector. This object is a scalar. This object is this or that. That is always imprecise. They should always say this particle is a scalar under the Lorentz group, transforms in the vector of an internal group, and is a spin in the spinor representation of another internal group. So just a statement like that, unless it's implicit, under which transformations you're talking about, is imprecise. So remember that when somebody tells you this is a scalar or this is a vector or something, you have to ask, well, with respect to what? Things are not just scalars. They are scalars with respect to something. Okay? Or they transform in a way with respect to something, not just in general. Okay, so let's stop here.